Come on in, everybody. I'm apologizing for being so late. I was literally doing something right up until time started. I see you guys are going ahead and chat me your first and last name. That's a good thing. Keep it up, please. I'm going to try to navigate to the page of my textbook so that I can continue on where we left off. So let's see what I can do with that. Still looking. A lot more people are coming. All right, we're up to 13 people. That's a good sign. Anybody have any questions before we get started? I'm just using this time, like I said, to navigate to the section of the textbook so we can get into chapter seven. We should knock out chapter seven today, and I'm going to push the due date back. In principle, I think you can finish chapter seven by Sunday, but I'm going to give you guys until Tuesday night to do that, just so you'll have ample time to ask me follow-up questions at our next meeting. And our next meeting will jump into chapter eight if we don't finish start it tonight. So let's go ahead and open the book to chapter 7. Anybody have any questions? Got another person. We're up to 14 people in here. Woohoo! And now we're trying to get to the textbook. Now, if I looked at my notes, uh-oh, I got the wrong thing up here. Let's see. That's what I want right there. And if I looked at my notes from last time, the last example we did was example 7.2. So that's where I'm starting off at, is going through examples beyond 7.2. I had also discussed with you specifically, let me make sure I get this open right. I had discussed with you specifically how the dot product was used. I even did a couple of examples of dot products, and I've hinted at how we're going to generalize the statement of work to be this line integral, but I haven't shown you any of that. So that's where we're going now. Uh, I'll ask one more time. Anybody have any questions before we get started? I did talk about conceptual example three. Just want to remind you, does the Earth do work on the moon? And of course, the short answer is no, it does not. And the reason why is because in order for the moon to go around the Earth like this, we know that the centripetal force, the force that keeps it going in a circle, points towards the center of the Earth. And at every point, that is exactly perpendicular, if we assume a circular orbit for the moon, at every point in the Earth's or in the moon's circular orbit, that force is perpendicular to the velocity. And since it's perpendicular to it, just like we saw the work done by gravity was zero because the work of gravity is this way, or the force of gravity is this way, whereas the displacement's at 90 degrees to it. And when you multiply it by the cosine of 90, that gives you an answer of zero. So, yes, it turns out that gravity does no work on a satellite that's orbiting the Earth, including the moon. That being said, in reality, the moon is does have an orbit that's a little bit of an elliptical orbit as opposed to a circular orbit. You can tell that because there's a supermoon and stuff like that that occurs when the moon is closest to us, and then there's times when the moon is quite small. And for instance, you get annular solar eclipses in that case because the moon isn't far enough away for us so that its face would completely block out the sun. So we get what's called an annular eclipse if it's lined up center to center, and that annular eclipse is basically the sun face being blocked by a smaller disk of the moon's backside, specifically backside or dark side. The dark side being the side that the sun's not shining on. So we know the actual orbit of the moon is a slightly elliptical orbit, and therefore, at some times there's a component of gravitational force that is actually somewhat parallel to the velocity. But it's not a huge one. So there is some work done on it in principle. Uh, Both positive work when it's being pulled from its farthest distance away, and then negative work when it's being pushed or reaching its farthest distance away. So when it's finished its farthest distance away, what's happening is the gravitational force is pulling a little bit to speed the moon up, and when it's farthest away, or when it's not farthest away, it's releasing a little bit or being a little less strong and allowing the moon to slip out. So hopefully that makes some sense to you guys. Let's go on now with example. As I said, we did do 7.2 already, and what I want to jump into now is example 7.4. It says using the dot product. So this is example 7.4. And it says a force shown in figure 7.7 has a magnitude FP equals 20 newtons and makes an angle of 30 degrees to the ground. Calculate the work done by this force using equation 7-4 when the wagon is dragged 100 meters along the ground. So equation 7-4 is basically A dot B is equal to the magnitude of A times, or excuse me, when they say equation 7-4, they're actually wanting us to do it the other way, which is AX BX plus AY BY plus AZ BZ. That's the equation 7-4 they're talking about. In order to make sense of that, we have to realize the actual figure and what it's made of. So what we,
Sir,
yes, I'm not sharing my
um,
screen yet.
yeah, that's yeah.
Thank you for that. I just realized I was sitting there. I was like, wait a second, I'm writing something down that they haven't seen yet. So yeah, let's do this. Uh, why is it not coming up? There it is. Thanks for catching me on that. I do appreciate it. I know sometimes it might seem like I'm trying to be smart aleck or anything, but it's not. I am very appreciative. There we are. Okay. So our diagram that we're talking about here is basically a box, and the box is being pulled by a force, FP equals 20.0 newtons. Now they only gave us two sig figs for this, so I wrote a dot zero and put an underscore under it so I can make sure that we at least can count those two as sig figs. The theta is 30.0 degrees, again with the theta underline, I mean with the last zero underlined. And ultimately, it's going to be pulled a distance d equals 100 meters. And that distance, of course, is horizontally. And what we want to do is calculate the work done. So what we're going to do is work is equal to F dot D. And this is true only when basically when the force is a constant and the angle between the force and the displacement vector is a constant and the displacement is a constant in one direction. If you have any of that stuff changing, you're going to have to do things to evaluate the force at each little part of the displacement that's not a straight line. So that's what we're shooting for here. In order to do this, what I'm going to do is convert this FP, this vector FP, into X and Y components. And this is 20-0 newtons is the magnitude. This is 30.0 bar degrees. Let me draw this in green because that's going to be the positive x direction. So this is FP sub x, which is equal to 20.0 newtons times the cosine of 30.0 degrees. And then this part right here is FP sub y, and that's equal to 20.0 newtons times sine of 30.0 degrees. Now we can go ahead and compute those. And notice I did go ahead and compute those, and I've already taken into account the signs. Notice the way that I've taught you guys to break your vectors down into components is you physically assign a sign to the components. In this case, I drew them both green because they're pointing to the right, which is normally the direction I call the positive x-axis, and it's pointing up, which is normally the direction I call the positive y-axis. So they're both automatically positive. And what are they? They're 20 times cosine 30, and that gives me 17.32 newtons. That's two extra sig figs, by the way, than I actually have. And again, I'll just put that that's positive. Now I'm going to say 20 times the sine of 30, and that should be 1/2, of course, so that makes it 10. So this is going to be plus 10.00 newtons for the y component. That means our FP vector can be written as 17.32 newtons I hat plus, excuse me, plus 10.0 newtons J hat, that's our FP. Now our D would be, it purely points to the right, so it only has an X component, and its length is 100 meters. So in this case, we're going to say it's 100.0 meters times I hat. So work, which equals FP dot D in this case, is going to be the 17.32 newtons I hat plus 10.00 newtons J hat. That's going to be dot producted. It's a difficult, weird word to say. Uh, by 100.0 meters in the I hat direction. Now, according to the formula, this should be FP sub x d sub x plus FP sub y d sub y plus FP sub z d sub z. And that, of course, gives us 17.32 newtons. That's the FP sub x times 100.00 newtons. That's the d sub x plus 10.00 newtons. That's the FP sub y times 0. That's the d sub y plus 0 times 0, because neither the FP sub y nor the d sub y are, neither the FP nor the d have a z component. So ultimately all we're left with is 1732 Newton meters. I don't know why I wrote a Newton there in a unit for 100. That was not supposed to be a Newton. That was supposed to be a meter. So there's a 0, and there's the meter. Did I do that on the other one? I didn't have to, so that was good. So this is a Newton, 1732 Newton meters. The 3 and the 2, of course, are not sig figs. So this should actually be called 1.7 times 10 to the third joules. That's equal to the work. Anybody have any questions on that one?
No, but can you wait a second before we go to the next page? It's a lot of writing.
Yeah,
Just
no
having
problem, no
trouble.
problem. Also, remember you can always do a screenshot if you ever get behind like that. Command Shift 3 works even on the Mac world and stuff like that. So, and you have a print screen in the non-Mac world, so you can do that as well, and it'll just take it to your clipboard. But no, I don't
Okay,
mind at all holding up for you. It's not a big deal.
okay, I caught up.
No problem. Thank you, sir. I appreciate that. Anybody else have any questions about how that was done or anything? So what we're working to, I'm just going to put it right here along the bottom of this page. What we're working to is the more robust formula for work, and that one's a little bit complicated, but it's basically this. Work is going to be the integral of F dot dl. And your book makes a point to say in this world, if at least if you're dealing with Cartesian coordinates, F is going to be F sub x I hat plus F sub y, J hat plus F sub z, K hat, and DL is supposed to be dx I hat plus dy J hat plus dz K-hat, that's exactly what you could put these formulas in. I have not found that to be necessarily the most useful way of doing it. On occasion, I have, but it's almost always a different way that I prefer to do it. So just be advised, you're not necessarily going to see this method come out necessarily in my examples, but any one of them you could force yourself to do it this way and then work it out. But again, that's just not the way I normally do it, and I'll explain it to you. This integral is not just a run-of-the-mill integral. It's an integral that would be covered in the last chapters of your calculus textbook. Normally, it's something that's covered, like I said, in the third semester of calculus, but I've never even been to a university where they were able to get to that material in Calc 3. I suspect if you went to UC Berkeley, which by the way did have five different Nobel laureates in this year's Nobel Prizes, they literally had five of the Nobel Prizes were faculty members. Five people that received Nobel Prizes were faculty members at UC Berkeley. Stanford's another type school like that. MIT's another one. Caltech's another one. Columbia, all the Ivy Leagues, all those things are really good universities like that. If you happen to go to them, one of those universities, then what you discover, as I did even at Chapel Hill, most of the students have already finished calculus by the time they get to college. Uh, and I say that at Chapel Hill because my first year teaching there as a grad student at Chapel Hill, the leader of the lab department came to us and said, "Well, I pulled the transcripts of all the students taking physics this semester, and this was supposed to be the algebra-based physics, and every one of them have had calculus. And because of that, we're going to teach all this lab and this class in general with calculus, even though it's technically an algebra-based physics class." So even at Chapel Hill, they had a whole first freshman class or that came in with calculus already. If you have that up front, then you might be able to get deeper into the normal classic calculus textbook. I've even seen some schools like University of Chicago is another good one. They sometimes have a whole different book for Calc 3. They'll have a book on differential forms or calculus on manifolds or something like that. So that's very normal. What we're doing here is called a line or a path integral. So this is a line integral or a path integral. And what I mean by that is you're basically supposed to have some ability to make an equation to represent the path you're following. And with that relationship, you can find a relationship between dx and dy. For instance, if it was a straight line that you're going along, dy over dx is the slope. So you could say dy is the slope times dx, and then that would have the dy carried over, and the dx would just be dx. But now you could actually integrate that. But that's one of the things you have to do is you have to evaluate the dx on the actual path that you're taking, and then the force has to be treated as a function of x, y, and z. You know, points in space have coordinates x, y, z. So you have to have a function of x, y, z in there, and you have to curtail those x, y, and z values so that they're representative of being on that path. So it sounds like a real nightmare to do, but in most cases, it's actually a lot easier than it sounds, as you'll see when we go along. The good news is that even if you didn't realize or didn't learn how to do a line integral, most of the time when you do this work calculation with an integral, you're still going to get the right answer because it's really hard to screw it up. Okay. That being said, there are some times where you'll consistently be wrong by a negative sign or something like that, and that all comes from the difference of a person that knows that the work is a line integral or path integral versus the person that just thinks it's an integral. So as we get into semester two, the Physics 242 class, I'll have more examples to be able to show you more complex ones where it's not as obvious. Whereas this Physics 241, most of the work that you calculate is a much more easy version. So we're going into section 7.3, and that's called work done by varying force. And that's where he makes the argument that the integral I just showed you is in fact the way you go about calculating the work done by a force. So the first example your book is working with is work done on a spring, And I'm going to give you a little idea of what that is. So what we know here is we're going to have a table top, say, and there's going to be a spring attached to the wall. And then that spring will have on it a mass M, say, and we'll assume this is like a frictionless surface or whatever. But the main thing we learn is that Hooke's law, this is Robert Hooke, the one of the nemesis of Isaac Newton and the predecessor of the Royal Society president. So he was the president of the Royal Society just before Newton became president of the Royal Society. And oddly enough, he's the only president of the Royal Society who we don't have a painting for. Many of us think that that's probably because Newton destroyed it because he didn't want him remembered in history. They did not get along very well. But what Hooke came up with was that the force, and he didn't do this for a spring. We use springs because the springs are easily, the stretch and compression of them are easily facilitated and measured. Whereas if you were using like an iron rod or a wooden 2x4 or something like that, the stretch or compression of a 2x4 or an iron rod can only be seen and measured for extremely large forces, and obviously that becomes kind of dangerous. But what he found was true for them as well, and that is that the force that a spring or a 2x4 or an iron rod applies when you stretch the object a distance x is directly proportional and in the opposite direction. So directly proportional means is F is equal to K times X, and then the opposite direction is why the negative is there. Because if you imagine for a second that our coordinate system is like this, where this is our positive x-axis, this is our negative x-axis, this is our positive y-axis there. Uh, when you move this mass over to, let's say, over to here, okay, then it has actually moved this distance x. That is a positive quantity. Therefore, if you multiply that positive quantity times a positive constant k called the spring constant, and it's something different, of course, if it's not a spring, but it is a spring in this case, so I'm going to go with it. But that's called the spring constant, and it's a positive value. So if you just multiply that positive x times that positive spring constant, you get F as some positive number. And if you're just thinking the magnitude, that's fine. But you should know that when I pull the spring out that way, sure enough, the force is going to point this way. So that's why that negative is in here, because it is a restorative force. But that is Hooke's law, and it's valid. It's valid for a huge value number of x values for springs. It's valid for less x values if you're talking about an iron rod or a 2x4 or something like that, because they all have their abilities, our maximum stretching amount where they don't come back afterwards. So, for instance, when you stretch a spring, if you stretch it too hard, you'll actually damage it in such a way that it'll never squeeze back up on itself. I'm sure you've had slinkies in your childhood and seen inevitably one of those little loops in the swinky will get a bend in it. That's what happened. You basically, well, sometimes it might not have been from overstretching. It could have just been from someone stepping on it, but the same thing would happen if someone stretched it beyond its elastic limit. So this equation holds for a lot more range values of x when you're dealing with a spring than it does so when you're dealing with a rod. But all of them have the potential to fail, and then they no longer obey F equals kx. So if I wanted to calculate the actual work done in stretching the spring from x equals 0 to x equals the number x, then I'd say work is equal to the integral of f dot dl. So the force is going to point, in fact, in the now. here I'm calculating the work I'm doing. So the force that's relevant is the force I'm applying to it, and the force I'm applying to this mass on the spring is a force pointing to the right. So I'm going to say that I have the integral of positive k times x times I hat because it points in the positive direction. Now, when you're doing a line integral, you have this dot product in here, and the dx or the dl has to be either used in that case to point the direction you're integrating, or you have to use the limits of integration to indicate the direction you're going. You can't do both. So what you do is one of them's just going to get automatically the positive coordinate direction, and the other one's going to get a sign to indicate that it's in either the positive or the negative direction. In this case, I am actually integrating in the positive x direction. I'm following the path in the positive x direction. So if I were to choose to let my dl define which direction I'm going, then I'd write it as positive dx I hat. Now, if I chose to do it, this is letting DL provide direction. Okay. If, on the other hand, I wanted the range of integration to indicate it, then I would say this is going to go from x equals 0 to x, and then I'd say kx I hat dotted with. Now, since I've chosen the limits of integration to indicate which direction I'm going from x equals 0 to positive x, then I'm supposed to take my dl and point it in the increasing coordinate direction, and the coordinate that's changing is the x coordinate. So lo and behold, I'm going to get just plain dx I hat. Now you can see in these two ways of doing it why you get the same answer either way, and therefore why students get the right answer even though they don't necessarily understand it's a dot product or a line integral or a path integral. So that's me showing you that. By the way, on that first case, I would then choose to go integrate from small x to positive x because that's the direction, that's the coordinate we're integrating along. So I would still say from x equals 0 to x equals x. Now, how do we do this? Well, the first thing I want to teach you is what I told you earlier is specifically that the dot product is a linear operator so that I can pull all the scalar stuff out in front, and that's going to be k times x times dx, and then I'm just going to leave the I hat dotted with I hat afterwards, and we already worked out that I hat dot I hat is 1, so we're done with that already. And the integral of kx dx is 1 half kx squared. So this is going to be 1 half k x squared, and I'm going to evaluate that at x equals 0 and x equals x. So the answer is 1 half k x squared. The same thing would happen here. It's just on the other version, it's just using limits of integration to indicate direction. Default equals positive slash increasing coordinate direction. And this is also the default, by the way, since I used the DL to indicate which direction I'm going, the 0 to X was the default direction as well. So I just get the same answer both ways. Does everybody understand that? All right. As you study a little further along, this will become more clear. And like I said, it's not that big a deal. It's rarely that you'll run into a work problem where you have to discern the difference between a line integral and a path integral. You just randomly get the right answer. So keep it in the back of your mind, think about it, or maybe even look at some problems in your calculus textbook that do line or path integrals and see if you can make some sense out of it that way. I'm going to go ahead and do example 7.5. It says work done on a spring. A person pulls a spring from in figure 710, stretching it 3.0 centimeters, which requires a maximum force of 75 newtons. How much work does the person do? So A, we're saying X is equal to 3.0 centimeters, and it requires a maximum force, so F max is equal to 75 newtons. And that's what's required to make it move that X equals 3.0 centimeters. And what they want to know is how much work. Okay, so they're giving us a little clue here. We know the formula. Oh, let me go ahead and read part B, and then we'll talk about that. B, if instead the person compresses the spring 3 centimeters, how much work does the person do? So that's part B. So solution is going to require us to know. You might not have thought of this part, but F is equal to negative kx, which becomes, if you're just talking about magnitude, just becomes F equals kx. You might not realize we have to use that, but we do. We also are going to use the formula that I just derived, which is 1 half kx squared. We are definitely going to have to use that. For part A, we realize that we want to calculate the work, so we need 1 half kx squared, but we don't have k. The whole purpose of them telling you, oh, it required a maximum force of 75 newtons was so that you could figure out what k is. So we're going to say, just taking the magnitudes, F is equal to kx, therefore 75 newtons is equal to K times 0.030 meters. Now, you can, in principle, have a spring constant in units of newtons per centimeter if you wanted, but I like to stick to the base units because there's some equations that just don't work unless you use the base units. And a lot of times you can actually use prefixes, but it's a little bit of work to trace it out. It's not something I'd recommend my 241 students to do, but by the time we get to electric circuits, I usually recommend my 242 students to do it. So in this case, we're going to see that K is actually 75 newtons divided by, now this is kind of neat. You can recognize that as 30 over 1,000, or you can recognize it as 3 over 100. I'm going to do it as 3 over 100 because you can see that I'm going to have 7,500 divided by 3, and obviously that gives me 2,500 newtons per meter. That's what the spring constant is. Okay. Now that I have the spring constant, I can say that work is 1 half kx squared. So that's going to be 1 half times 2,500 newtons per meter times 0.030 meters quantity squared. And when I do that, I get times zero point 0.5 times 0.03 squared. And that's only 2 sig figs, so this is going to be 1.125 joules is the work done. And that's in stretching the spring. We'd have to call that 1.2 because the sig figs require us to round it at one decimal place. But I think that's actually 1.1, not 1.2. Sorry about that. Now, in the other case, there's really no difference. In this case, B, oops, in this case, B, we're compressing it. So what we could say there is work is equal to the integral of F dot dl. So using the actual integral, I know the force I'm going to apply to compress it is actually going to be to the left. So the force is negative k times x times I hat. And then here is a case where I could actually use the actual differential dl as the indicator of what direction I'm going, or I can use the limits of integration. If I use the limits of integration this time, which is not what I did last time, then I'm going to say I'm going to integrate this from x equals 0, or excuse me, from x equals negative negative 0.030 meters to x equals 0. And then my dl has to just point in the positive coordinate direction. So I'm going to say that's dx I hat like that. Okay. So if I do this now, then the negative should come out in front and the k should come out in front, and I get the integral of x dx I hat dot I hat, which obviously is just 1. So this is going to give me, and again, I'm integrating it from negative 0.030 meters to zero point 0.0 meters. This is going to give me negative 1 half k x squared, and I'm doing that from 0.030 meters negative to zero point 0.0 meters. That means I'm going to get negative 1 half times 2500 or joules, excuse me. Yeah, it's newtons per meter. That's what I was, sorry about that. Newtons per meter times zero point 0.0 meters squared minus negative 0.030 meters squared. And you see, lo and behold, I'm still going to get a positive quantity, and it will be positive 1.125 joules is equal to the work. Any questions on that? So I could have done it the other way. I could have let my DL indicate the direction I'm integrating, in which case I would have written negative dx I hat, but then my range of integration would have been from 0 to negative 0.030. That would again give me exactly the same answer I got before, but that's the key point. This is an example where you actually had to, if you chose to inspect the intricacies, you'd be forced into doing something a little bit more than normal by changing the range, the direction in which we're integrating and stuff like that. But in doing so, now you've seen both cases. So you either got to, when you're doing a path or a line integral, you either got to let the DL indicate the direction you're going with by a positive or negative sign or whatever it takes to make sure you go the direction along the path that you said you're going, and then the range of integration would go from small coordinate to large coordinate. Or you can make the range of integration tell which way you're going. So you'd go from the starting point, integrate to the ending point, but the DL would point in the positive coordinate direction in that case. So that's your two choices. Anybody have any questions on that? Okay, let's look at example 7.6, a more complex force law. So this is example 7.6. And it says the force is a function of x. So we've got f of x is equal to f0 times 1 plus 1/6 x squared over x0 squared. And they gave us the values of f0 and x0. F0 is equal to 2.0 newtons. X0 is equal to 0.0070 meters. And we're going to go from x1 is equal to 0.010 meters to x2 is equal to 0.050 meters, and they want to know work is equal to question mark. So in this case, we're going to do work is equal to, again, we're just using the formula. Work equals the integral of f dot dl. Okay, so that's the formula I'm using. I'm going to say work is equal to the integral. Now, this is purely an x direction force. It only depends on x, and we're going to go on the assumption since we're moving from x1 to x2 that it's only moving in the x direction. So the force is really going to be F0 times 1 plus 1 6 x0 squared in the bottom times x squared, rewriting it that way. I'll just say times I hat. That's all dotted with dx I hat. It's obvious that we went from x equal 0.01 to x equal 0.05. That's the positive direction, so I could indicate it by letting the dl point in the positive direction. And now I'm going to integrate in the direction of increasing x value, which is what the default that we have to do when we've chosen for the other one to indicate the direction. So this is going to be from x1 to x2, which I'm writing that instead of the numbers. So again, we can treat this like the linear operator it is. I'm going to pull the f0 out in front because that's clearly a constant. I'm taking the integral of 1 plus 1 over 6 x0 squared, which is just a constant, times x squared, times all of that times dx, and then times I hat dot I hat, which is 1. So now what we're going to do is keep the f0 right here, and I'm going to integrate the first term, which is 1 dx. So the first term just becomes x, and I'm going to evaluate that from x1 to x2. Ooh, x2. And now I have the plus symbol, the integral of 1 over 6 x0 squared. Now I'm integrating x squared. That's going to give me 1/3 x cubed. And that's going to be integrated from x1 to x2, and that should be it. So now I can go ahead and plug in these numbers. I know that the F0 is 2.0 newtons. I know that I can put a square bracket around this too. I know that this is going to be 0.050 meters minus 0.010 meters plus 1 over 6 times 3 is 18, so I'm going to put the 18 down there, and then the x0 was 0.0070 meters squared. So that's just the constants that were out in front, and now I have to multiply that by 0.050 meters cubed minus 0.010 meters cubed. I can't fit that last bracket, but I think y'all can figure out what's done there. So I'm going to move along. Obviously, I've got 2.0 newtons times 0.040 meters. 1 divided by parenthesis 18 times 0.007 squared in parentheses gives me plus 1,134, and that unit should be meters to the negative 2 power. And also I only had 2 sig figs, so the 3 and the 4 are not sig figs. And now I take 0.05 and I'm going to raise that to the third power. That's going to give me 0.000125 meters cubed minus 0.01 again cubed. That's going to give me 0.0000010 meters cubed, like that. So I'm going to say 0.000125 minus 0.000001 gives me 2.0 newtons times 0.040 meters plus 1134 meters to the negative 2 times 0.000124 cubic meters. Now we can start multiplying. So zero point zero 0.04 times 2.0 is 0.08 joules. That takes care of that term. And then I multiply 1,134 times 0.000124, and that gives me plus 0.1406, and that gives me, of course, units of newtons times meters, which is also a joule. So I can now say 0.1406 plus zero point zero 0.08 is 0.2206 joules is the work done. Anybody have any questions on that one? Whoa, that's definitely different from what the book got. See what I made a mistake. Let's see. It looks like I cubed everything. That should be fine. Anybody get a different answer than me? I don't think I've ever remember finding an error here, so in the book, so I'm pretty confident it's my mistake. I just don't know where I made it. 0.050 minus 0.01 is 0.040. That's good. Let's try the 1 divided by, let's just clear everything. Okay, 1 divided by 6 times 3 times 0.007 squared in parentheses. Yeah, that's still 1,134, so I'm okay with that figure. Uh, and then zero point zero 0.05 cubed is 0.000125 meters cubed, so I know that's right. Uh, 1/100th cubed would be 1 times 1 times 1 over 100 times 100 times 100, which would be a million, so it'd be 1 over a million, and that is zero point zero 0.01 cubed, 0.01 cubed, and that's tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, 1/1 millionth, so that is right as well. Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths. 0.000. Still get 0.1406 for that. Oh, I never multiplied by 2. That's what it is. I must have forgotten to multiply by 2. Let's see if that makes a difference. 0.28 plus 0.08. Ah, that's it. Yeah. I just forgot to carry my 2. So this answer, everything was done right except I forgot to carry the 2. This answer right here should have been 0.2812, and then this answer becomes 0.3612 joules. So The physics I did was right. The arithmetic I did was right, but the algebra of distributing that two evidently only went to the first term because I'm a goober. Anybody have any questions on that one? All right, here's the work energy principle, which I've hinted to already, so I wanted to explain that to you now. So this is called the work energy principle. Whoa. I spelled work with an E on the end all of a sudden. I don't remember doing that before. I think it's because I was thinking of the work energy principle. Work energy theorem or principle. And it basically is come about by this. Let's take Newton's second law. The summation of the forces is equal to mass times acceleration, like that. Okay. Now we know that work net is equal to the integral of F net dotted with dl, like that. But F net is the summation of all the forces. So we can go ahead and say this is going to be the integral of the summation of the forces dotted with dl, like that. And we can go further still and use the other side of the equation. I'm going to say instead of sigma f, let's replace that with m dv dt because A is dv dt. And then that all will be dotted with dl, like that. Well, you can actually do this. I will point out to you that yes, we use the symbol dv over dt as the symbol for the derivative of the velocity with respect to time, but the individual dv's and dt's are actually physical things in mathematics. We call them one forms. So they actually can be moved around, multiplied, and that sort of stuff. So we've been sort of acting like we're making up stuff when we do differential equations and all that kind of stuff, but it's actually a reality. You're completely able to do that. And what I'm going to do is exchange the positions of the dl and the dv. So I'm going to get integral of m dl dt dotted with dv. Now, can anybody guess what dl dt might be? Think about its units. dl dt, L is just like an X or a Y or a Z. So what would dl dt be? About V. So that's actually what it is. The dl dt is the actual velocity. Because of that, we now can reduce this to equals the integral of mv dv, because the dot product between v and dv is just v times dv, because dv is parallel to v. So the cosine theta doesn't come into play. And the integral of v dv is 1 half mv squared evaluated at v0 and v final. So the net work is equal to 1 half mv final squared minus 1 half mv initial squared. And we define a quantity K as kinetic energy. And it's 1 half mv squared, in which case we now have W net is equal to delta K. And that's the work energy theorem, or the work energy principle. Okay. The net work done on any system is equal to the change in kinetic energy. So right now, you guys are sitting at some desk or some car or somewhere, hopefully not in a car moving, but you're sitting somewhere looking at a TV screen and your velocity is almost certainly zero. Okay. Last time you were with me, you were sitting probably in the same place, but definitely your velocity was probably zero again. So right now, I can tell you for a fact that the total amount of work that's been done on you since last class to now should be zero because in both cases your kinetic energy is zero, and therefore the change in kinetic energy is zero. So, any questions on that? All right, so let's look at example 7.7 now that we know this. 7-7, kinetic energy and work done on a baseball. A 145-gram baseball is thrown so that it acquires a speed of 25 meters per second. So M is equal to 0.145 kilograms. Notice I went ahead and converted it from grams to kilograms. V initial is zero because it's thrown, so it acquires a speed. You know it had no speed before, so V zero is equal to 0 meters per second, but V final is equal to 25 meters per second. So we have that. And what we want to know is A, what is the kinetic energy? And B, what was the net work done on the ball to make it reach the speed if it started from rest? So W is equal to question mark, and specifically W net. So that's our question. Well, what we know is W net is equal to the change in kinetic energy. So we'll use that, and we know kinetic energy is 1/2 mv squared. So we know that. So that's what I'm writing down to begin our solution. Now I'm going to start with A. Kinetic energy is 1/2 times 0.145 kilograms times 25 meters per second squared. I'm going to write this as K final. So I'm going to say zero point 0.5 times 0.145 times 25 squared gives me 45.3. Let's call that 31 joules. Notice kilogram meter squared per second squared gives you kilogram meter per second squared, which is a Newton, and then times a meter because it's kilogram meter squared per second squared. So it's a Newton meter, which is a joule. So that's right. That's equal to K final. I'll circle that. And now in part B, they want to know what the net work done is. W net is equal to the change in kinetic energy, which equals kinetic energy final minus kinetic energy initial. Notice that triangle I drew. That's the capital delta from, the Greek alphabet, and that means change in. And generally speaking, unless we explicitly tell you otherwise, it's always final minus initial. So whatever symbol is to the right of that triangle, you're supposed to take and write that symbol with a final subscript minus that symbol with initial subscript, and that's what the delta is. So that's why I wrote it this way. We happen to know specifically that the final kinetic energy was 45.31 joules, and the initial was zero point 0.0 joules. Therefore, W net is 45.31 joules. And that's it. Anybody have any questions about that? All right. Let's look at example 7.8. It's an estimate problem. Yes, sir.
Please hold it for
No
a
problem.
second there. I tried to screenshot, but I I
I
couldn't find the
probably moved it.
screenshot
I
thing.
saw myself moving instantly. I was like, that's going to bother him.
Yeah.
No problem.
Yeah, I just need a sec. All right, I got it.
No problem. All right. Let's look at example 7.8 now. It says work on a car to increase kinetic energy. How much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? So work is what we want to know. We want to go from M, We know that's 1,000 kilograms, so I'm going to pretend like that's going to be 4 sig figs. And we're going to go from V initial is equal to 20.0 meters per second. That's me trying to claim the zero as a sig fig, to V final, which is 30.0 underbar. Again, trying to make it sure it's 2 sig figs. And what we want to know is how much net work is required. I'll put the little net on it as well. So W net is equal to the change in kinetic energy. Therefore, W net is equal to 1/2 m times V final squared minus V initial squared. That's the easiest way to write it so that I don't have to repeat calculations. So that's 1/2 times 1000.0 kilograms times 30.0. I'm going to leave off the units here, minus 20.0, like that. And that gives us W net is equal to, I'm going to do the 30 squared. That only has 2 sig figs. That means 30 squared is 900. So that's only good to the tens place. And then 20 squared is 400. So that's also only good to the tens place. So I'm going to say 900 minus 400 is 500. And that's only good to the tens place. So now I'm going to multiply that 500 times 1,000 times zero point 0.5, and that's going to give me 250,000 joules. And technically, I only have 2 sig figs there, so all these guys are not significant. So I really need to write that as 2.5 times 10 to the 1, 2, 3, 4, 5, 10 to the fifth joules is equal to W net. Any questions on that? All right, let's look at example 7, 9. In this case, we're actually stopping a car. So it says work to stop a car. A car traveling 60 kilometers per hour can brake to a stop within a distance of D equals 20 meters. See figure 717A. If the car is going twice as fast, 120 kilometers per hour, what is the stopping distance? Assume the maximum braking force is approximately independent of speed. Okay. So, if V0 goes to 2 times V0, which is of course 120 kilometers per hour, then what is the stopping distance? Okay, I'm going to say this is V0 sub 2 and D2. So what we discovered was work net is equal to your change in kinetic energy. So W net is equal to delta K. That's just our solution. So that's the equation we're going to use. And what we found was that the work net could equal, in the first case, so I write a 1 by that, that's going to be equal to delta K, which is K final minus K initial, which is 0 minus 1/2 of. Now, in this car case, we could approximate the mass of the car to just be, well, actually, we'll just leave it as M. And then we're going to say V0 squared. And we know that that has to be equal to the force done by friction. And that force is, of course, the normal force times the coefficient of friction, which is just the friction force, times the distance. So I'm going to say this is the friction force times the distance. So what we have, and that's also a negative, by the way, because the friction force points this way when the car is going that way. So the 180, the cosine of 180 gives you the negative 1. So what we have is negative 1 half m v0 squared is equal to negative fd. So that means F is actually equal to m v0 squared over 2d. That's for the first part. And I haven't put any numbers in because I think I can work this without numbers. You're welcome to put numbers in, but notice they didn't give you a mass. What we do have, though, for part two is we have V02 is equal to 2V0. Now, as they said, assume the maximum braking force is approximately independent of the speed. So they're saying that that friction force is independent of the speed, so we can assume that it's the same friction force. So with that in mind, I'm going to say that F2 is equal to F1, which equals mv0 squared over 2d, but they want to know the distance in this case. So in this case, we're going to say, well, F2 is equal to m2v0 squared over 2, and then this distance will be d2. Okay, so looking at that, I can see that the square of the 2v0 is going to give me 4. Then I have 2v0s or mv0 squared over 2d2 like this. And what I recognize now is that this has to be equal to mv0 squared over 2d. So I can now divide both sides by m. That cancels out that. I can divide both sides by v0 squared. That cancels out that. And then I can divide both sides by 2 or multiply both sides by 2. And that'll cancel that out. And what I now have is 4 over d2 is equal to 1 over d, which is the original one, so we could call that d1 if we wanted. But the main thing is that d2 is going to be equal to 4 times d. So that's the result we really wanted. If you double the speed, it's going to take you 4 times as much distance to come to a stop. And that is a principle that we should know about driving. If you're, for instance, driving at 50 miles per hour and then you enter a school zone where the speed limit is 25, then your velocity, if you don't slow down, your velocity is twice as fast as it's supposed to be, and therefore it takes you 4 times the braking distance. And of course, 25 is a big enough braking distance for you to still possibly injure a child. So obviously, if you had to take 4 times as much distance, then you're going to have a much bigger chance of injuring a child. So you don't want to mess with that at all. Anybody have any questions on that one? So the big deal that we're learning here is the friction force necessary to stop is directly proportional to, or actually I should say, the distance of stopping is directly proportional to the square of velocity. That's the big rule that we're coming up with, and hopefully you see that from what I just worked. Anybody have any questions on that one? All right, I'm going to do example 710 now. We still got a little bit of time left, so let's do example 710. Oh, did you get all that? Anybody? I flipped really fast again, so I wasn't paying attention. Seems like everybody's okay. I'm moving along. Thanks, Ryan. Okay, 710. It says a horizontal spring has a spring constant K equal 360 newtons per meter. How much work is required to compress it from an uncompressed length x equals 0 to x equals 11.0 centimeters? And B, if a 1.85 kilogram block is placed against this compressed spring and the spring is released, what will the speed of the block what will be the speed of the block when it separates from the spring at x equals 0, ignore friction. And then C, repeat part B, but assume the block is moving on a table as in figure 718, and that some kind of constant drag force, 7.0 newtons, is acting to slow it down, such as friction or perhaps your finger. So let's write down the information we know. We were given the spring constant, K, is equal to 360. I'm going to put my foot down and demand that be 3 sig figs, newtons per meter. And part A, we're going from x equals 0, and we're going to compress it to x equals 11.0 centimeters. And they want to know how much work is done. Then for part B, they want to say M equals 1.85 kilograms is the mass. And we want to see if you place that mass against a compressed spring and the spring is released, what will be the speed of the block when it reaches the 0 stretch mark? So we want to know V final equals question mark. And then for part C, they want to repeat it with FD equal to 7.0 newtons, and they want to find the final velocity like that. So solution in this case, what we want to know is we're going to use the fact that the work done in compressing a spring is 1/2 kx squared. We've already derived that. We can use that formula over and over and over again. So now we're going to do that. And then we're going to try to figure out how much work is done against friction for that last part. But let's go ahead with part A. So with part A, we're going to have basically the entire potential energy that came, or the entire, excuse me, potential energy, we haven't learned that yet. The entire work that went into compressing the spring, we're going to assume that the spring can do that much work on the mass. So that means 1/2 kx squared will be equal to the final kinetic energy of the mass. So 1/2 mv final squared is what we got here. We can see that the m or that the 1/2s cancel out, and I get v final is equal to the square root of k x squared over m, and that of course is the square root of k over m times x. So I'm going to say that's the square root of 360.0 newtons per meter divided by 1.85 kilograms. A newton per meter is a kilogram per second squared, so that just leaves a per second squared under the square root. And then I got to multiply this by, uh, it's supposed to be 11 centimeters, so I'm going to say this is 0.11 meters. And that should give us the velocity v final in meters per second is square root of 360 divided by 1.85, and that gives me 13.94. Now I only had 3 sig figs there, so I'll put that's 13.949. And that's just plain seconds to the negative 1 power. Oops, let me write that a little better. It looks like it's on top of it. So that's seconds to the negative 1 power. Ah, darn it. And then I'm multiplying that by 0.11 meters, and that gives me 1.5345 meters per second is V final. So that's the final velocity that we get in part A. In part B, or excuse me, oh, I actually just did part B, not part A. Stupid me. So we're going to call that part B. Part A is going to be work is equal to 1/2 times 360.0 newtons per meter times 0.11 meters squared. That amount is zero point 0.5 times 360 times 0.11 squared. That gives me 2.178 joules with one number underlined. So that's the kinetic energy, or that's the work done, 2.178. I could have just set that equal to 1/2 mv squared and solved it that way. I did the same thing, I just did it symbolically. Now I need to take part C, and in this case, the 1/2 k x squared is going to be used to not only get the 1/2 mv final squared, but it's also going to be used to take the friction force, which we call F drag, times the distance, and it's going to steal some of that energy away from it. So that 1/2 kx squared, part of it's going to the 1/2 mv squared, but the rest is going to the FD times the zero point 0.1, or FD times, let's just call it x. So 1/2 mv final squared is equal to 1/2 kx squared minus FD times x. Well, the 1/2 kx squared is 2.178 joules minus 7.0 newtons times 0.11 meter. So this is 2.178 minus, so this gives me 1.408 joules, like that. And that's equal to 1/2 mv final squared is equal to 1.408 joules. So V final is equal to, I'm going to take the 1.408 and multiply it by 2. Now I'm going to divide that by the mass, and the mass is 1.85. And now I'm going to take the square root of that result. So I take the square root of 1.522, and that gives me 1.234 meters per second. You can see it definitely went a little slower this time, and that's exactly what we expect. And we have now finished chapter. Yeah, I got the right answer for that. We have now finished chapter 7. There's some more stuff in there that's worthwhile reading, but we've done all the examples, and you guys are free to go. It's right on time. I'll wait for the last person to leave in case anybody has any questions. But like I said, you're free to go. Make sure you chat me your first and last name if you haven't done so already.
Thank you. Have a good night.
You're welcome. See you, Zach.
Have a good night.
You too.
Thank
Thank
you.
you. Thank you. See, some of my students came from class today. That's cool. Any of you folks have any questions?
Hello, Mr. Young. I have a question
Yes.
about C of 710 real fast.
Okay.
So I understand that the work net of 1/2 kx squared will equal 1/2 mv final squared. But whenever we add the friction force,
Mm-hmm.
is that also
Ah, yeah, so the
I-
reason I'm adding it is you can imagine that basically the spring, by us putting work into it at compressing it, it has a certain amount of energy in joules associated with us compressing it that way. So that is the 1/2 kx squared. That's the total energy we have to work with in part C, that had to not only provide the kinetic energy, which is the 1/2 mv final squared, but it also had to provide the work done by the friction force. And the work done by the friction force is just the force times the distance. It technically would be negative, but I put it on this side, so it's being added to the quantity. I could have put it on the other side with the 1/2 kx squared, but it had been subtracted from it. Either one of those would be acceptable. So, for instance, I could have written it like this. I'll write it in red. I could have written 1/2 kx squared minus fd times x, and then that would equal 1/2 mv final squared. That would be acceptable as well, but you see the reasoning is the total energy that the spring has is the work I put in it. And in the part C, we have to not only speed the object up by increasing its kinetic energy, but we also have to combat friction, which would be the Fd times x. That's the work done by the friction.
Okay, that makes a lot more sense. Thank you for clarifying.
No problem. I'm glad that helped. I didn't know what I was going to say if it didn't come clear to you.
Really fair. Well, have a good night.
You too. Thanks. Sawyer, Shayla, James, or Ryan, anybody have any questions?
Yeah, I got a question. I got here late, 'cause I was running late from getting out of work, and then there was traffic. I was just
No
wondering
problem.
if your lectures are posted to YouTube or what I can do to catch up.
Yeah, I do post them to YouTube, and we actually started a little late anyway, so you didn't really miss too terribly much. But yeah, every time I meet you guys, I one take this notes that I took, I upload them to my Google Docs, which you have a link to in the Canvas course, and I upload this to YouTube. I usually don't do it till the morning after, but it will be on my YouTube channel by tomorrow morning, if not tonight.
Okay, thank you.
No problem. You're welcome. James or Sawyer or Shayla, anybody have any questions? They might not be here, so I'm going to go ahead and call it a day, everyone. Thanks for coming. I hope it was helpful to you. Have a good day.